Welcome back. In this module, we are going to discuss probability theory. Probability theory might be a very familiar concept for most of you. Some of you might have studied in your high school, some of you might have studied in your early years of college. And in this session, it's going to be a revision of basic concepts which are relevant in the context of machine learning. So, to start with, what do we mean by probability theory? It provides a consistent framework for the quantification and manipulation of uncertainty. In machine learning predictions, we are never certain whether our classification is correct, whether our classification is wrong. There is no absolute answer whether something is a dog or something is a cat. So it's always a good idea to assign uncertainties with it. If you are only 50% sure that something is a cat, then you should always give the uncertainty measure regarding your decision. And for this, we need the probability theory. Now, what do we mean by probability? So probability provides a measure of what are the chances of occurrence of an event. Either maybe because we have observed several runs of the same event or the same experiment in the past, or because we have some other type of information about the process by which those results are generated. Now, looking at these examples on the right, the first one is of dice. If we assume that the dice is fair, when I say fair, we assume that each of these sides have an equal probability of occurrence, then the probability that 3 will occur when a dice is thrown is 1 by 6, that's 16.6%. Similarly, if we were asked the probability that if we pick 2 days randomly from a week, what's the probability that they will be Saturday and Sunday? That's here. Probability that we will have all the red balls here, that's 5 by 20, that's 25%. So why do we need it? It facilitates making optimal decisions even under very ambiguous scenarios. And where does this ambiguity come from? The ambiguity can be of two types. It can be noise from the measurements, and the other one can be because of the finite size of the data set. If you have only very few samples in your data set, you can never be sure what the underlying model is. And that unsurety that we are referring to is actually the ambiguity. And there we assign uncertainty through the probability. Now, there are two different points of view when we talk about probability. One is frequentist view. And what is frequentist view? Frequentists look at probability of an event as the limit of its relative frequency in many trials. A frequentist will always look at the results of an experiment. They will perform the experiment several times. They will look at the results, and based on the results only, a frequentist will assign the probability. I'll be explaining this with another example, but let's try to first understand the formal definition of this. Now, as I said, when we are dealing with probability in the context of frequentist view, we look at well-defined random experiments and we look at their results from multiple trials. A hypothesis is typically tested without being assigned a probability. If a frequentist is given an experiment, and if she has to define the probability of occurrence of certain result in that experiment, they will wait for first looking at the observations from multiple trials, and then only they will assign the probability. Before testing the hypothesis, they're not going to assign any probability. That's the way of looking at from a frequentist point of view. The other way of looking at probability is the Bayesian view. In the Bayesian view, it is interpreted as reasonable expectation representing a state of knowledge or as quantification of personal belief. So in the Bayesian perspective, it's more about an opinion. If you have certain experiment, and if it is asked what the probability of occurrence of certain result in that experiment, a Bayesian point of view would first gives a certain probability based on an opinion, and that we generally refer to as prior probability. And then after testing the hypothesis, we tend to update the probability to reach our final probability. So when we look from a Bayesian point of view, we first assign a probability to a hypothesis. That probability might not be exactly correct. That also depends on the amount of data, but a Bayesian would assign probability to a hypothesis even before, even without running the experiments. So I guess now we see the two views here, the frequentist view and the Bayesian view. The biggest difference between them is that the frequentist will see at the results of the experiment, but the Bayesian will not. And let's try to understand this with this simple example. I have a coin. I flip the coin. Let's say I have the coin. I flip the coin and I hide the result here. Now, if I ask you what's the probability that it is a tail, I can see the result in front of me. It is there. I can see the result. And I'm asking you, what is the probability that it is a tail? Now, if I mean, there are two answers to this. Some of you might say 50%. If you say it's 50%, then you are giving this answer based on some previous experience, based on some, I mean, it's your opinion. I did not give any information whether the coin is biased or there is any external condition that is going to affect it. But that was your opinion that you gave, and that is a Bayesian way of looking at the problem. If you are a frequentist, how would you respond? A frequentist would say, I don't know whether it's a head or tail. You might know it, but as long as I don't see it, I will not answer. If the frequentist sees a head, he will say the probability that it is a head is 100%. If a frequentist sees it as a tail, they would say the probability of the tail is 100%. And if you perform the same experiment 10 times and the 11th time you show the frequentist, they will evaluate it based on the result they have seen in all the observations. So a frequentist will not give an opinion unless they have seen the results of the experiment. A Bayesian will put an opinion. That's the difference between them. Some of you might have started liking the frequentist view. Some of you might have started liking the Bayesian view. But which one is better? Which one do you need? And to be fair, there is no one view to choose. Both of them have their own advantages, and it depends very much on the problem that you're dealing with that you would choose it. Now, another important concept that comes as soon as you start dealing with probability is random variables. What is a random variable? A random variable is used for numerical description of the outcome of a statistical experiment. Let's say we have an experiment of flipping a coin. Then the random variable in this case is the result that we see on the coin. It can be a head or it can be a tail. So similarly, if we are throwing a dice, the outcome of the dice is a random variable. The types of random variables, there are two types of random variables, discrete and continuous. We will look at each of them one by one. But to start with the discrete random variable, the two experiments that I mentioned just now, the dice and the coin, we see them on the right. And to start with the discrete random variable, it has a finite sample space. For example, the results of the experiment can be 1, 2, 3. The results of a certain other experiment can be A, B, C. For the experiment that we show on the right top, this one, the results can be 1, 2, 3, 4, 5, 6. So discrete set of results that we can see as an outcome to this statistical experiment of throwing the dice. Then in this case, the two results that we can see are the head and tail. These discrete sort of experiments that you observe, they are characterized for discrete random variables. So the discrete random variable has finite sample space. We saw the examples already. The probabilities are given here. So that's it about discrete random variables. Now, that was the case of one random variables. But in general, when we are dealing with complex experiments, we can have hundreds, we can have thousands of random variables. And in this slide, we discuss the scenario of two random variables. So on the left, we have two random variables, X and Y. These can be any random variables, but to just to add, let's say, a context. Let's say we have two dices and we throw both the dices together. Then one random variable can be the result of dice 1, the other can be the result of dice 2. Similarly, let's say we I have a dice and a coin. We throw the dice, we flip the coin together. The result of the dice can be random variable x. The result of the coin can be random variable y. So here we have x, which has m possible outcomes. Here we have y, which has l possible outcomes. For the case of coin and for the case of dice and coin, then m will be 6, l will be 2. But we are not dealing with those examples here. We just take a general case. And now we translate these two random variables here on the grid. And now we see that we have y here. So we put l is equal to 3. And we have x here. So we put m is equal to 5. Now, what does this each cell represent? There were several experiments performed, and each cell here represents the number of times this combination has been observed. So the number of times we observed xi and yj together, that is nij. So that is what each cell represents. And what does this ci? All the cases where we observed the value of xi together with different values of y, when they are summed together, that is ci. So sum across this entire column. And rj is the sum across this entire row. Just to reiterate, this cell, any cell, nij represents the number of times xi occurred with yj. So for example, xi can, if it was 6 and 2, the dice and the coin, it could be, for example, number of times we saw 3 on the dice and heads on the coin. So similarly, that's what nij would refer to. Now we try to build some of the popular definitions around it. So we start with joint probability, assuming that the overall number of trials was this capital N, the uppercase N that we see here. Let's say this is the total number of trials. So the sum across all the cells in this grid will be N. Joint probability is defined as the probability that this xi, that the random variable x held the value xi and the random variable y got the value yj. The probability of that thing is referred to as joint probability. So joint probability is the probability when x is equal to xi and y is equal to yj occur together. And from this grid, it can be written as nij by capital N. The next one is marginal probability. What do we mean by marginal probability? To understand that, I would like to define the term marginalization. Marginalization across a certain random variable implies elimination of that random variable from the joint probability. That is one way to look at it. So when we say marginal probability x is equal to xi, it implies that if there are 2 random variables, if there are 5 random variables, if there are 10 random variables, we marginalize across all the other random variables and we only retain x. So what it would mean is that the probability that x is equal to xi, and from the grid we see that for x is equal to xi, the total probability is the sum of this cell and this cell. So the entire sum, that is ci, divided by capital N. That's what we see here, marginal probability of x is equal to xi. Similarly, the marginal probability of y is equal to yj, that is the sum across this whole thing, that is rj. So rj over n. That is what marginal probability is. Now we do some maths here. We got nij. So we had this joint probability from equation this. We had joint probability of x equal to xi, y equal to yj is equal to this. We bring the capital N on the left side. So we get this nij is the joint probability of x and y multiplied by n. Now from the figure, we see that ci is equal to summation of nij. So ci is sum of nij across all possible values of j. So across all possible values of j. So we write ci is equal to j is equal to 1 to l summation nij, right? Now I'll move it a bit here. Now when we plug this in the marginal probability equation, we get probability of x is equal to xi is summation over all the values of y, the joint probability. This is what we get. And this equation is actually referred to as the sum rule. So what sum rule defines is when the probability of x is equal to xi can be written as summation across the probability of y is equal to yj for all values of y. So we sum across the entire thing. That is a sum rule. So now we write one more equation here. Now we again, So next we move to conditional probability. So what conditional probability means is the probability that y is equal to yi when x is equal to xi. That is referred to as conditional probability. So if you're not familiar with the concepts of probability, I would like to again clearly show you the difference here. This is joint probability when x is equal to xi and y is equal to yj. Here we have capital N here, right? This probability is with respect to the total number of trials. But when we say conditional probability, we want the probability that y is equal to yi when x, no, so this should be actually j. So y is equal to yj when x is equal to xi. So that can be written as nij divided by ci, because the total number of times x is equal to xi, that is ci. So we have ci here. Then the total number of times among those that y is equal to yi, so among all the ci's, the y equal to yj is this one. So nij divided by ci. That is the conditional probability. Now, again, doing some maths around this equation, we have the joint probability. We have the joint probability written as this here. Now, what we do is we take the value of nij from the equation of conditional probability. So that will be equal to this conditional probability multiplied by ci. And we plug it in here. So the conditional probability multiplied by ci. And then we have n here. That gives us that the joint probability of x equal to xi and y equal to yj can be stated as the conditional probability that y is equal to yi when y is equal to yj when x is equal to xi multiplied by the marginal probability of x is equal to xi. And this is referred to as product rule. So the product rule states that the joint probability of the two random variables can be stated as the conditional probability of occurrence of one of the random variables with respect to the other random variable multiplied by the marginal probability of the other random variable. So that's the product rule. So these are some of the important concepts in probability theory. So random variables, the multiple random variables, joint probability, marginal probability, conditional probability, product rule, sum rule. Now let's try to see each of these in this simple experiment. So I would like you to look at it very carefully. This experiment, what we see here is a grid where on the x-axis we have the random variable x, on the y-axis we have the random variable y. Now, this random variable x, it can hold multiple different values. So the number of grids defines the number of possible values for random variable x. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So x has 9 discrete possible values. Let's look at it like this. Now, on the y-axis, we have the random variable y, and it is allowed to take two different values. So y is equal to 1 and y is equal to 2. So x can hold 9 values, y can hold 2 values. And there is an experiment performed 60 number of times, and we show the results here. So we show the results here, and let's say that the discrete value of and every sample, the grid that it falls is the value of the random variable x, and from here the random variable y. So what it means is that there are 3 times that y is equal to 1 and x is equal to 1. Similarly, there's only one time that x is equal to 7 and y is equal to 1. We can look at it by counting the dots. We can look at the number of times it happens. And when you divide by 60, you get the probability of each of these. So if I were to ask you what is the probability that x is equal to 5 and y is equal to 2, so it would be 1, 2, 3, 4, 5 here. So total x is equal to 5 and y is equal to 2. So that would be this cell. So there are 1, 2, 3, 4, 4 dots divided by 60. That would be 1 over 50. So that's how we look at it. Now, we can estimate the joint probabilities by looking at each of these boxes, count the number of dots and divide by 60. That's the joint probability. If we want to compute the marginal probability Px, so going back to the concept of marginalization, if we want to compute the marginal probability of x, we need to sum across all the other random variables. So we have to marginalize across y. That would mean that when we say marginalize across y, what we can do is we can sum up the dots across this dimension. So we eliminate the random variable y, and to convert it into probability, we just have to divide by 60. So although we don't have these numbers here, we will, in this case, this will be 3 by 60. Then we have 6 dots, no dot, 6 by 60, then 3, 3, 6, whatever it is, dash by 60. Then we sum these number of dots with this and we put it here by 60. Similarly, for this case, it will be like 5 dots here, 5, 3 dots here, 5, 3, 8, 8 divided by 60. And here we have 3, 3, 6, 2, 8, 1, 9. So 9 divided by 60. So we see here, right? 8 by 60 and 9 by 60, which is slightly higher. So that is what we do when we want to compute the marginal probability Px. Similarly, when we have to compute the marginal probability Py, we just sum across the x dimension. So for y marginal probability of Py equal to y2, we sum across all x. So we sum all the number of points here, divide by 60. So this is 1. We sum all the count the number of points along this dimension and then divide by 60. That is what we see here. That's the marginal probability Py. So that was marginalization. Now, if I have to compute the conditional probability that of x comma y, when y holds a certain value. So in this case, let's say we want the conditional probability of x when y is equal to 1. So what we would need to do is, we first need to take only the cases where y is equal to 1. So that would mean we eliminate this whole thing. We forget this entire part. So that is y equal to 1. Among them, we now need to quantify the probability of x. So now when we are computing y is equal to 1 on the lower part, we don't need to look at the total 60 now. We will need to look at only the cases where y is equal to 1. So let's say this is 32. I'm not going to count it exactly, but let's say this is 32 for y is equal to 1. Now, if we have to count the probability of x equal to 1 when y is equal to 1, that would be 3 by 32. Similarly, x is equal to 2 when y is equal to 1 would be 3 plus 3, 6 divided by 32, and so on. So that is the conditional probability. Similarly, we can compute the conditional probability of x when y is equal to 2, or the conditional probabilities with respect to y. So with respect to x, so we can compute conditional probability of y when x equal to 1 or 2, 3, 4, 5, 6, 7, 8, 9. So that is what conditional probability is. I hope with this example, the concept of joint probabilities, marginal probabilities, and conditional probabilities is clear. Now, we talked about discrete random variables. Now let's also talk about continuous random variables. The difference between discrete and continuous random variables is that continuous random variables have infinite sample space. So if there's a range of numbers, an interval, these variables can take infinitely many values within that interval. And the probability distribution is for continuous random variables, it is defined by a density curve. So this is an example of for continuous random variables. And for continuous random variables, probability is not defined at a point. So if you would ask me what is the probability of x is equal to c, that would be 0, because for that is how conditional probabilities would be defined for probabilities would be defined for continuous random variables. For any point, the probability is 0, And if you want to compute probabilities, they are always defined on an interval. So the correct way to ask is, what is the probability that the continuous random variable x holds value between a and b? So it's a bit of error in the notation, but let's say here, what is the probability that the random variable x holds value between the interval a and b? And that is just the area under the curve between the value a and the value b. That is how the probabilities are computed for continuous random variables. So like I said, now if we look at it again, for a certain point, if you ask me what is the probability that x is equal to c, I would say 0, because the area under the curve at for just one single point would be 0. And then positivity refers to the probability for any range will always be greater than equal to 0, because the area under the curve, the lowest can be 0. It's always greater than 0, and the overall probability is the for if you sum across the entire curve, that would be equal to 1. So that's what we see here. And then we can, it's very common to compute cumulative distribution. So if you ask me what's the probability that x is less than 10, so it would be just the random variable x less than equal to, put 10 here, and that is the summation from minus infinity to x dk. So k is a different integration variable that we use here. So that is what is cumulative distribution. So that's all about continuous random variables. They don't. This is the only difference that they have in terms of differentiating them from the discrete random variable. But overall, the concept of probabilities is still the same. So now putting all the rules of probability that we read for discrete random variables and also translating them for the continuous random variables, the positivity for both cases, the probability for, in the discrete case, the probability of certain x, in the continuous case, x will be an interval. For both cases, it will be greater than equal to 0. For additivity, the probability that the random variable x belongs to a subset A will be summation across the probabilities for every element of A. So every possible value of x in A, we just sum across the probabilities. That is additivity for discrete random variables. For continuous random variables, you just take the area under the curve between A and B. Normalization says that the summation across all possible outcomes, the probability of the summation of probabilities across all the outcomes will be 1, and that's the same with continuous random variables. Then we can sum the probability to compute the marginal probability of px. We can sum across all the other random variables. Similarly, we can do it for continuous random variables. And then the product rule states that for the joint probability can be stated as the product of the conditional probability and the marginal probability. And that's what we have here for both cases. So those are the rules of probability that we have for discrete and continuous random variables. And that brings us to the Bayes theorem, a very simple but very important concept in machine learning. So what Bayes theorem is? Principled way of calculating a conditional probability without the joint probability. So in the previous slides, we saw that we have the joint probability and we can use the joint probability and also the marginal probability. We can estimate the conditional probabilities. But what Bayes theorem gives is, in some cases, it might not be straightforward to compute these joint probabilities. So Bayes theorem gives you a way to compute these conditional probabilities without going towards the joint probability. And so deriving it from the product rule, we have this, the pxy, the joint probability is the conditional probability multiplied with py. If we use the symmetry property of the two random variables, we can write this. So probability of x when y occurs multiplied by probability of y, that is equal to probability of y when x occurs multiplied by px. And then we do some shuffling around, we obtain this, that the probability of y when x is happening is equal to the probability of x when y occurs multiplied by the probability of y, and then we divide it by x. So we brought this term here. So that is what Bayes rule is. So now we see that if we want to obtain this conditional probability, we can obtain it from another different condition term here and these two terms here without going towards the joint probability. That is the Bayes rule. It sounds just a simple equation, but it is very handy for several cases where you cannot compute this term directly. So you You can estimate these three terms easily, and then we obtain this term through this equation of Bayes rule. Now here in this equation, the py term, this is referred to as prior probability of y is equal to y. The term on the right left, this is called posterior probability of y. We are interested in the distribution of y. So the conditional probability of the random variable y holding to obtain this value of y from the distribution when x is given, that is referred to as the posterior probability. Then we have this px when y is occurs, that is referred to as likelihood of x given y, and the term px is referred to as the evidence for the random variable x to hold the value of x. Now, if you note here, we call this term as the likelihood of x and this term as the posterior probability. And from symmetry property, we said that they are more or less the same things. It's just that the flipping of random variables. So why would you call it this one as posterior probability and this one as likelihood? This question was also asked in the live lecture, and I would like to stress upon this point. Let's take the case. This it actually depends very much in the context you're talking about, but let's take the case that we are looking at a distribution of y, and let's say x is a set of parameters. X is it's a set of parameters, and y is the distribution that we are interested. So what this term says is, when we have a certain value of x, what is the probability of y happening? And this is actually it defines the chance of outcome for different values of y given x. So it is referred to as probability. If you sum across all the values, so if y is the distribution you are interested, if you sum across all the values of y for a certain x, that is going to be 1. So that is why it is referred to as probability. It's the chance of each outcome of y for a certain x. Now here what happens is, if let's say if this x is the set of parameters that characterizes the distribution of y, and we have an observation y for the random variable y. If we have an observation, what is the chance that this observation is what is the chance, how we interpret this term is, what is the chance of occurrence of this observation when we have this parameter? So when we have x, what is the chance of occurrence of this parameter? So we interpret it other way around. If we have this observation, what is the chance of this observation to have occurred when we have this value of x? So in this case, if we take y1, y2, y3, y4, different values of y for a fixed x, it sums up to 1. But in this case, for every different observation, so if we take the x, if we sum across this, if we have x1, x2, x3, x4, for a certain value, for x1, we get a different distribution of y. For x2, we get a different distribution of y. So for different values of x, this observation corresponds to a different distribution. And if you combine the chances of each of these y's, they will not sum up to 1. So it is defined, this term defines the chance of occurrence of, it defines the chances of a hypothesis. So it's hard to define this in this context, but this term, if you sum across all the values of x, this will not be 1. So this is not a probability term. It's not the best way to explain it directly. I would recommend, if you're really interested to understand more on what the exact difference is between this probability term and the likelihood, I would recommend looking at some video of statistics, because the edge between statistics and probability, that's what defines the difference between this posterior probability and likelihood. But overall, from a experimental point of view, this sums up to 1. So that and it is a probability, but this will not sum up to 1, this likelihood term. So this is the likelihood of x equal to x when y is equal to y, and this is the posterior probability of y is equal to small y when x is equal to x. Now, we have read a lot of concepts. Now let's try to look at this simple example to give you an idea of how these different concepts can be used. So what we want here is we have two boxes. We have a red box, we have a blue box, and the greens here denote apples, and the orange here denote the orange. So starting with, our problem statement is to find the probability of the box color given the observed fruit. If we were asked what is the probability of any fruit when the box color is given, if I give you the box color red, the probability of apple is 2 by 8. If I give you the box color blue, the probability of orange is 1 by 4. So it's straightforward. But the question now is, what is to identify the probability of the box color given the observed fruit? It can still be computed here, but I mean, it's still a relatively difficult task. So we start with building on all the concepts, and you will see how simply you can get the answer to your question. So starting with defining the random variables. So the random variables in this case are the fruit and the box. So we have the first random variable f, which is apple and orange. The other random variable is the box, which is red and blue. So we have two random variables, each has two possible outcomes. Now we start with the prior distribution of the boxes. So the prior distribution, P of box is equal to red is equal to 4 by 10. This is something which is known. And then we have P of box is equal to blue is 6 by 10. So let's say this is known from some external sources. We start with computing the conditional probability of fruit given box. So probability of fruit being orange given box is equal to blue. So box is equal to blue, fruit being orange is 1 by 4. That's what we have here. Fruit being orange, box is red. That's 6 by 8. Fruit being apple, box being blue. That is 3 by 4. And then the fruit being apple, box being red. That is 2 by 8. So 1 by 4. So those are the conditional probabilities. I hope up to here it is clear. I mean, it's quite straightforward. You just count from the picture and you put the numbers here. Now, we compute the marginal distribution of fruits. So first we want the probability of fruit being apple, and we marginalize across the box. So if you recall from the marginalization concept, what we want is that probability of fruit being I think I made a mistake here. So we are actually let me check. Yes, so we are going to compute the marginal distribution of fruits here. What we do here is we want the marginal distribution of fruit being apple. So that would mean we have to sum across joint probabilities of fruit being apple and box being blue or box being red, and we have to sum across all of those boxes. So we are skipping a step here, but if you look at it closely, we want to compute the marginal distribution. So we want fruit being apple and box being, let's say, blue. So that would be, ideally, that would be joint probability of fruit being apple and box being blue plus joint probability of fruit being apple, box being red. So that would make it summation along the boxes, the joint probability of fruit and box. Now, what we have here now is that we express the joint probability using the product rule as the product of the conditional probability multiplied by the marginal probability. So if you do this rewriting on your side, you would simply find that this marginal distribution of fruit being apple can be stated as summation across all the boxes, the conditional probability multiplied by the marginal probability. So that would come down to 1 by 4 into 4 by 10, that is 11 by 20. Now, similarly, if we want to compute the probability of fruit being orange, and the marginal probability of fruit being orange. So that would be, uh, I'm missing a bit of figure here, but that would be fruit being orange, box being red, into marginal probability of box being red. So that is the joint. This term, this is the joint probability of fruit being orange and box being red, expanded using the product rule. So this term plus the fruit being probability of fruit being orange when box is blue multiplied by the probability of box being blue. This term. So when we apply the sum rule on this, we obtain the marginal probability of fruit being orange and box being marginal probability of fruit being orange irrespective of the box. So there is some text missing here, but that boils down to 9 by 20. So now we would also expect that the marginal probability of fruit being apple and the marginal probability of fruit being orange, they sum up to 1, right? And that's what we see here. So we have 11 by 20 and 9 by 20. And when we add them, we obtain 1. So now we know the random variables, we know the prior distribution of the boxes, we know the conditional probabilities, and we know the marginal probabilities. With all this, putting all this information in a more beautiful manner here, we have the prior probabilities here, the marginal probabilities here. Now this is the information that we have. What we wanted to compute was the probability of box color given the observed fruit. So that we refer to as the posterior probability of box color given observed fruit. So now you see the posterior term. This implies we are going to get the Bayes rule in now. Now we want the probability of box being red when the fruit is orange, and with the Bayes rule we express it as the probability of fruit being orange, box being red, multiplied by the probability of box being red, divided by the probability or marginal probability of fruit being orange. So when we put these numbers from the top, this is the conditional probability. We don't have it up here, but we had it in the previous slide. So if you quickly, so we have these numbers here. When we put those numbers in there, we obtain 66.7%. So that is the probability of box being red when the fruit is orange. Similarly, probability of box being blue when the fruit is orange is, we put the Bayes rule, we put the numbers in there, and we obtain 33.33%. This term we could have also computed directly from here, and from there the probability of box being blue when the fruit is orange is equal to 1 minus probability of box being red when the fruit is orange. So that is just 1 minus 2 by 3, that is 1 by 3. So we obtain the same result. So this verifies that is correct. Similarly, we can also compute the probability of box being red and box being blue when the fruit is apple, and that is quite straightforward, but I will skip it. But now we see that we wanted this thing. We wanted the probability of box color given the observed fruit. We started with the prior, defining the random variables, computing the prior probabilities, moving to the marginal probabilities using the product and the sum rule together, and then finally using the Bayes rule to compute the posterior probability. This is one example where these concepts together make these difficult probability concepts very straightforward to compute. But in machine learning, we have more difficult concepts, and we will see in the later lectures how these probability terms and Bayes rule together are helpful in the context of machine learning. But that's all for now in this lecture. I hope with this the concepts of probability are clear.